Welcome back to Physics 3740 at the University of Utah. Today we're going to we're going to derive the Schrodinger equation in spherical coordinates. This is basically a mathematical exercise, and it does appear in a little bit less detail in your book, that is Harris, and many other books, but I think it's worth it to go over this. I'm going to omit some steps, but most of the steps that I omit can be done pretty readily by yourselves. Okay, so let's talk about spherical coordinates, or sometimes called polar coordinates or spherical polar coordinates. And so spherical or polar coordinates are defined according to this figure here. Okay, so what we have is we have our normal Cartesian axes x, y, and z, and we define our spherical polar coordinates with respect to these axes. And so if we imagine that we have our point that we're interested in describing in polar coordinates, we define our origin, which is clearly here, and we define an angle theta, which is with respect to the positive z direction. Okay, so theta, as is indicated here, is with respect to the positive z direction, and so it only goes from 0 to pi. Okay, as I've indicated here, and then with respect to if you drop a line from that point down to the xy plane, then we can define an angle phi with respect to the x-axis, okay, which can go all the way around, so it's phi is between 0 and 2 pi. And then r is just the distance from the origin to the point, okay. And with this we can then define three unit vectors in this coordinate system. We can define the r hat unit vector, which again is basically just pointing along the line from the origin to the point. Okay, and it's always pointing outward. Okay, and or from origin to point. There is the theta hat unit vector, which basically is tangential to the sphere that this point lies upon, and which is described by the angle theta. And then finally there's the phi. This is hard to see in this perspective, but there's the phi hat, which again would be defined by this little circle here, which circumvents the sphere and pointing along the direction of phi. Okay, so the way that you would, so normally when we define a point in Cartesian coordinates, we would go out some distance x, we would go this way some distance y, and then we would go up some distance z. And then here in polar coordinates we go out from the origin some distance r. We have an angle theta, which is again with respect to the z-axis, and then an angle phi with respect to the x-axis when you drop a vertical line onto the xy plane. Okay, so that's basically how you define polar coordinates. Hopefully you all have seen that. That's kind of a review. We can convert between rectangular, that is Cartesian coordinates, and polar coordinates. So we can r is defined to be just the distance, so it's x squared plus y squared plus z squared square root. Theta is the inverse cosine of the distance z here divided by the distance r, square root of x squared plus y squared plus z squared, and phi is equal to the inverse tangent of y over x. Okay, and you can also define x, y, and z. We can do the inverse definition over there.